This is the next part of the lesson Gravitation of class 10 science 1. Now, before this, we have studied about Kepler's laws. Now, these Kepler's laws, the first law is the orbit of a planet is an ellipse with the sun at one of the foci. So we know now what is an ellipse. An ellipse has two foci. So on one focus there is sun, and uh, the planet is orbiting in elliptical orbit around the sun. Then the next law, second law, is the line joining the planet and the sun sweeps equal area in equal interval of time. So suppose this line in some interval of time goes from here to here. The time required is t. Then suppose we now think that it starts from here, then in the same time t it will go from here to here. Note that this shaded area and this shaded area are the same. Then as it goes away from the sun, this area also is the same. However, the central angle decreases, or focal angle, let us say, not central angle, because that is not a center, it is a focus. So focal angle decreases. This focal angle is more when it is near the sun. The planet is near the sun. The focal angle is less when the planet is away from the sun. This focal angle is still less when the planet is very much away from the sun. So this is how the movement of planet is. And then the third law is the square of the period of revolution around the sun is directly proportional to the cube of the mean distance of a planet from the sun. So mean distance means, now here here the distance from here, let's say this distance is r1, this is r2, this is r3, this is r4, etc., etc., and it increases and finally it again decreases to r. So various observations if you take of this r and make an average, that is called mean distance from the sun. Now there is one more method which we can think of. Mean distance from the sun. How to explain this? Because the distance is always changing. So you think of these two figures. This is a circle and this is an ellipse. If suppose this is an ellipse and its area is something, if we so let us now think this way. This is an ellipse. Suppose I am drawing a very rough sketch. This is f1 and this is f2. These are two foci. Now if we now this is a long ellipse like this, oblong. If this focal distance foci are brought near each other and So the same ellipse will, its oblongness will decrease, and its height will, in other words, its major axis will decrease and its minor axis will slightly increase if the area has to be the same. So like that, if the foci come near and near and near, finally there will not be two foci but one center, and it will be a circle. And area of this circle and area of this circle is same. Then we can say that this distance r is the mean distance from the focus. So in this Kepler's third law, it is said the square of its period of revolution. Period of revolution means time required for one revolution, that is capital T, around the sun is directly proportional to the cube of the mean distance from a planet from the sun. Means the mean distance of this planet means, if this ellipse is to be considered as a circle, or if we consider a circle of the same area as that of the ellipse, then that radius of circle will be what we call the mean distance of the planet from the sun. So in other words, this Kepler's third law, we have to look at it like this: T is equal to period of revolution of the planet, and R is equal to mean distance of the planet from the sun. So we can consider, instead of ellipse, a circle of that mean distance, which will remain now constant, and it will be radius of that circle. So now whatever we speak of ellipse, let us now consider a circle of that the radius equal to that mean distance, and then we say that T square is directly proportional to R cube, or in other words, T square upon R cube is equal to constant. So this is Kepler's third law. Now after Kepler comes Newton, and how Newton formulates his inverse square law, that is, the force is inversely proportional to the square of the distance between two objects, that inverse square law. Now here it is given in textbook, but it is quite confusing, and here I think there is printing mistake also. So I will like to draw your attention to this proof. So the force, centripetal force, we have seen in the previous part of the previous video on the same lesson, that this force is equal to mv square upon r, where m is the mass of the object performing uniform circular motion. Now this entire thing about is now about uniform circular motion. We are no more speaking about an ellipse, but we are speaking about a circle with its radius equal to mean distance from the sun. So if this is the object of mass m, now in this case it is planet of mass m, and v is the linear speed of the object, means how much distance on circumference it travels in 1 second in unit time, that is linear speed. So this f is equal to mv square upon r. This we have already proved in the previous part of the video. Now this v is what? If t is the time period of revolution, so in one revolution it goes linear distance equal to 2 pi r, that is circumference of the circle. So 2 pi r upon t is that v. So m into 2 pi r upon t bracket square upon r. Now if we square it, this t square comes in denominator, and 2 pi square comes to be 4 pi square. 2 square is 4 and pi square is pi square. And this square of r is r square. This m does not get squared. This m is as it is and this r is as it is. Now I multiplied this numerator and this denominator by r. So here I get r square and here I get r cube. So here I get a quantity r cube upon t square. Now according to Kepler's law, we know that t square upon r cube is k. Now here I have used that small r, so t square upon small r cube. This t is period of revolution, and according to Kepler's third law, t square upon r cube is k. So obviously this r cube upon t square is 1 upon k. So I put that k over here. Everything else remains same. 4 pi square m upon r square k. So here this r is changing. R is variable. So I put it like this, 4 pi square m upon k into 1 upon r square. Now this 4 is constant, pi is constant, m is constant, k is constant, so all this becomes constant. So force is equal to constant into 1 upon r square. We can write statement of variation as force inversely proportional to r square, and this is what is called inverse square law. This inverse square law can be derived from this Kepler's law, t square upon Kepler's third law, t square upon r cube is equal to k, and this derivation of inverse square law, which is there in the Newton's law of gravitation. The force of gravitation is inversely proportional to square of distance between two bodies. This can be derived from Kepler's third law, and here they have tried to give it, but something is missing. This 4 m pi square upon r square is equal to, this is equal to side is wrong. This into this multiplied by this, and this is 1 upon k. So this multiplied by 1 upon so 4 m pi square, okay, this is okay. But in this 4 m pi square upon k is constant, so f is inversely proportional to r square. Here they have made a mistake over here, so it has become confusing. So I have written it again on board, the correct version of the proof, and I hope you understand this now. So like this, you have to so to summarize, we have to consider some points over here. Point number one is that you are not speaking about ellipse but about circle. Why? You have to understand that every circle is an ellipse, but every ellipse is not a circle. So This is an important thing. Every circle is an ellipse, but every ellipse is not a circle. So here we are speaking about circle of the radius equal to mean distance of the planet from the sun. And so we apply the law of uniform circular motion here. Now in elliptical motion, that linear speed does not remain constant. We have seen that what is how do we define speed in case of that ellipse, that the line joining sun and the planet sweeps equal area in equal interval of time. That defines speed. But here when that ellipse is considered as a circle, then we can apply this equation F is equal to mv square upon r, which is valid for what we call UCM, that is uniform circular motion. So there is a the textbook has not explained this, so there is a big confusion that Kepler's law speak about ellipse, and this explanation here what they have given, it starts from mv square upon r, and it speaks about uniform circular motion. Now how does uniform circular motion come in Kepler's laws? Because Kepler's laws speak about ellipse, and here we are speaking about circle. Then how is that? The so that part we should understand as it is a circle of the radius equal to mean distance of the planet from the sun. Then it gets linked to uniform circular motion, and then we find a smooth proof of inverse square law from starting from Kepler's third law. So I hope you understand it, you write it again on your own, and digest this concept very much. This is very important concept, inverse square law, derivation of inverse square law from Kepler's third law. Best of luck.